Hello there, and welcome to another journey into the cosmos. Tonight, we're drifting back to the very beginning of everything, to the moment when time itself was born and space first began to unfold. We're exploring the Big Bang, that extraordinary event that created not just our planet, not just our solar system, but every star, every galaxy, and every particle of matter that exists today. It's a story so vast and so profound that it can carry you gently into sleep while filling your mind with wonder about our cosmic origins. As you settle in tonight, let your breathing slow and your thoughts soften. We'll be wandering through some of the most fascinating discoveries about how the universe came to be. From the first fraction of a second when everything was smaller than an atom, to the moment when light first traveled freely through space, each fact we explore will be like a gentle. If you enjoy these waves carrying you deeper into rest cosmic journeys and would like more content to help you drift off to sleep, feel free to like and subscribe and share your thoughts in the comments below. But for now, all you need to do is get comfortable and let the story of creation itself wash over you. The Big Bang wasn't actually an explosion in space. When we hear the term Big Bang, our minds often picture a massive explosion happening somewhere in empty space, with matter and energy flying outward from a central point. But this image, while dramatic, isn't quite accurate. The Big Bang was something far stranger and more profound. It was the expansion of space itself, the birth of the very fabric of reality. Imagine trying to picture the surface of a balloon as it's being inflated, but instead of the balloon existing in a room, the balloon is all there is. There is no room around it, no outside space for it to expand into. The surface of the balloon is reality, and as it grows, every point on that surface moves away from every other point. This is closer to what happened during the Big Bang. Space didn't explode into existence within some larger container. Space itself came into being and began to stretch, carrying matter and energy along with it. Every point in the universe was moving away from every other point, not because they were flying through space, but because space itself was growing between them. It's a concept that challenges our everyday understanding of how things work, but it's one of the most beautiful insights we have about the nature of reality. The entire observable universe was once smaller than a proton. In the beginning, everything we can see today, every star in every galaxy, all the matter that would eventually form planets and people and everything else, was compressed tinier than the smallest into a region, far particle we can imagine one of the building blocks of atoms. A proton is already incredibly small, but the early universe was even smaller than that, perhaps as small as the Planck length, which is so tiny that it defies comprehension. To put this in perspective, if a proton were scaled up to the size of a marble, the Planck length would still be smaller than a proton is in reality. And yet, within this impossibly small space, all the energy and potential for our vast cosmos was contained. The temperature was so extreme, the density so incredible that the normal rules of physics as we understand them simply didn't apply. It was a realm where quantum effects dominated everything, where the very concepts of time and space were still forming. Time itself began with the Big Bang. Perhaps one of the most mind-bending aspects of the Big Bang is that it marks not just the beginning of space and matter, but the beginning of time itself. Before the Big Bang, there was no before. This isn't because we don't know what happened earlier, but because earlier doesn't have meaning when time hasn't started yet. It's like asking what's north of the North Pole. The question itself doesn't make sense because north stops having meaning at the North Pole. Einstein's theory of relativity showed us that space and time are woven together into what physicists call space-time. If space began with the Big Bang, then time began with it too. The universe didn't start ticking at some moment within already existing time. Instead, the Big Bang was the moment when the cosmic clock first began to tick at all. Every second that has passed since then, every moment of history, every sunrise and sunset, has been part of the unfolding story that began in that first instant when time itself came into being. The first second contained more history than all the rest of time combined. That initial second after the Big Bang was the most eventful period in the history of the universe. More fundamental changes occurred in that first second than in all the billions of years that followed. The universe went through phases of existence so different from anything we know today that they seem like different realities entirely. In the first tiny fraction of that first second, the universe underwent, where it expanded faster, a period called inflation, than the speed of light. This might that nothing can travel faster than light seemed to violate Einstein's rule, but it wasn't matter moving through space that fast. It was space itself stretching at that incredible rate. During this brief period of inflation, the universe grew by regions smaller than an atom became a factor that's hard to even express in numbers we can relate to. A larger than a grapefruit in less time than it takes light, the end of that first second, the universe had to cross the nucleus of an atom. Bilette enough for the first atomic nuclei to form. Protons and neutrons, which had been created earlier, finally came together to form the nuclei of hydrogen and helium. This process, called Big Bang nucleosynthesis, created almost all the hydrogen and helium in the universe. These are still the most abundant elements in the cosmos today, making up about 98% of all ordinary matter. The cosmic microwave background is the afterglow of creation. About 380,000 years after the Big Bang, something remarkable happened. The universe had been opaque up until this point, filled with a hot plasma where light couldn't travel freely. Photons would bounce off electrons constantly, creating a cosmic fog. But as the universe expanded and cooled, it finally became cool enough for electrons to combine with atomic nuclei, forming the first neutral atoms. This event, called recombination, suddenly made the universe transparent to light. The photons that were freed during this moment have been traveling through space ever since, gradually cooling and stretching as the universe expanded around them. Today, we can detect this ancient light as the cosmic microwave background radiation. It fills all of space with a faint glow that represents the oldest light in the universe, a baby picture of the cosmos when it was just 380,000 years old. This background radiation is remarkably uniform, but it contains tiny fluctuations, slight differences in temperature from one region to another. These tiny variations were the seeds that would eventually grow into the galaxies and galaxy clusters we see today. In a sense, when we look at the cosmic microwave background, we're seeing the blueprint for all the large-scale structure in the universe. The universe was once too hot for atoms to exist. For the first 380,000 years after the Big Bang, the universe was so hot that atoms couldn't hold together. Anytime an electron tried to orbit an atomic nucleus, the intense radiation would knock it loose again. This meant that the early universe was filled not with atoms as we know them, but with a plasma of free-floating protons, neutrons, and electrons, all moving about independently in the cosmic heat. The temperature during this period was thousands of degrees, hot enough to ionize any atoms that might try to form. It was only when the universe had expanded and cooled to about 3,000 degrees Kelvin that atoms could finally form and remain stable. This temperature might still sound incredibly hot, but it represented a dramatic cooling from the trillions of degrees that existed in the first moments after the Big Bang. During this plasma era, the universe would have glowed with brilliant light, but that light couldn't travel far before being scattered by the free electrons. It was like trying to see through a thick fog, except the fog was made of subatomic particles and filled all of space. Only when atoms formed and the fog cleared could light finally travel freely across the cosmos. The Big Bang created the perfect recipe for stars. The Big Bang didn't just create space and time and energy, it also established the precise conditions needed for stars to eventually form and shine. The balance had to be just right. If the universe had expanded too quickly, matter would have been spread too thin for gravity to pull it together into stars. If it had expanded too slowly, everything would have collapsed back in on itself before stars could form. The Big Bang also created exactly the right mix of matter and energy. About 75% of the ordinary matter created was hydrogen, the simplest and lightest element. About 25% was helium, which is slightly heavier. This ratio was crucial because hydrogen is the primary fuel that powers stars, while helium plays important roles in stellar evolution. The trace amounts of lithium that were also later created would play a part in more complex stellar processes. But perhaps most importantly, the Big Bang created tiny density fluctuations, regions that were slightly more dense than average. Over millions would amplify of years, gravity-ify these small differences, causing the denser regions to attract more matter and become even denser. Eventually, these growing concentrations of matter would become dense enough and hot enough for a nuclear fusion to begin. Stars would ion the first sight, lighting up the universe for the first time since the cosmic dark ages began. Most of the universe is made of things we can't see. On the universe of the most surprising discoveries about the Big Bang and created is that the ordinary matter we're familiar with, the stuff that makes up stars and planets and people, represents that exists. The rest is made up only about 5% of everything of mysterious only through their gravity that we can detect substantiational effects. About 27% of the universe consists of something called dark matter. This isn't ordinary matter that just happens to be dark. It's an entirely different of substance that doesn't interact with light or ordinary matter in ways we can directly observe. We know it exists because we can see its gravitational influence on galaxies and galaxy clusters, but we don't know what it's actually made of. Dark matter may have been create the Big Bang through during processes is dark energy, which makes up about we don't yet fully understand. Even more mysterious, this 68% of the universe appears to be a property of space itself, causing the expansion of the universe to accelerate over time. The more space expands, the more dark energy there is, which causes even more expansion in an ever-increasing cycle. Like dark matter, dark energy seems to have emerged from the conditions established during the Big Bang, but its true nature remains one of the deepest puzzles in modern physics. The Big Bang explains why the night sky is dark. This might seem like a strange explaining thing to me, but there's actually a famous puzzle called Olbers's paradox that asks why space appears black at night. If the universe were infinite and fill infinite number of stars that within hasht bin, then eining forever, every direction you look should show you a star, making the night sky as bright as the surface of the sun. The Big Bang provides the answer to this puzzle. The universe isn't infinitely old, so light from distant stars hasn't had infinite time to reach us. There are regions of space so far away that their light simply hasn't had enough time to travel to Earth since the Big Bang occurred 13.8 billion years ago. This creates a cosmic horizon beyond which we cannot see, ensuring that the night sky remains dark between the points of starlight. Additionally, the expansion of space causes light from very distant objects to be redshifted, stretched to longer wavelengths that our eyes can't detect. What might be invisible have light when it left a distant galaxy billions reach of years ago might us as infrared radiation that we can't see without special instruments. In this way, the Big Bang not only created the universe we see, but also determined what canon. It cannot see of every atom in your body was forged in the aftermath of the Big Bang. The hydrogen in the water you drink, the calcium in your bones, the iron in your blood, all trace their origins back to that primordial moment when the universe began. In those first few minutes after the Big Bang, the intense heat and pressure created the conditions necessary for the first elements to form through a process called nucleosynthesis. During this brief window, lasting minutes only about 20, the universe was essentially a cosmic furnace. Protons and neutrons collided and fused together, creating the nuclei of the lightest elements. Most of the hydrogen and nearly all of the helium in existence today was forged during these first 20 minutes. The universe was so dense and hot that nuclear reactions occurred everywhere at once, creating a cosmic chemistry set that would provide the raw materials for everything that came after. But the heavier elements, the carbon that forms the backbone of organic molecules, the oxygen we breathe, the nitrogen in our DNA, these weren't create the Big Bang itself. They would come later, cooked in the heart stars that would have massive live and die over billions of years. Yet even these stellar furnaces owed their existence to the precise conditions established in those first moments after creation, when the universe set the stage for the long, slow process of cosmic evolution. The Big Bang created space with a built-in speed limit. One of the most fascinating aspects of our universe is that information and matter cannot speed of light. This cosmic travel faster than the speed limit isn't just that a rule particles happen to follow. Woven into the very fabric of space, it's Wedim itself, established in the fundamental structure, the Big Bang, created during travels, light at approximately 300,000 kilometers per second, and this speed represents something deeper than just fast photons move. It's the speed at which cause and effect can propagate through the universe. When you flip a light switch, the electrical signal doesn't travel instantly through the wire. When you see a distant star, you're seeing it as it was years ago because the light took that long to reach you. This speed limit creates a kind of cosmic communication delay that everything affects, from the smallest quantum interactions to the largest structures in the universe. The implications of this speed limit are profound. It means that our observable universe has boundaries, regions beyond which we cannot see because light hasn't had time to travel from since there to here, the Big Bang. It also means that simultaneity, the idea of things happening at the same time, becomes depending relative on your frame of reference. The Big Bang didn't just create space and time, It created a universe where space and time are intimately connected through this speed limit. The fundamental universe went through a period when it created its after-own darkness. The cosmic microwave background was released and the universe became transparent. You might expect it that would remain bright and visible. But instead, the universe entered what cosmologists call the Dark Ages, a period lasting hundreds of millions of years, when the cosmos was indeed dark and empty of light sources. During this time, the universe contained only hydrogen and helium gas, slowly clumping together under the influence of gravity. There were no stars yet, no galaxies, no sources of light except for the gradually cooling afterglow of the Big Bang itself. The temperature continued to drop as space expanded and the cosmic background radiation faded from visible light to infrared to microwaves, leaving the universe in an era of cosmic night. This darkness wasn't empty though. Invisible dark matter was pulling ordinary matter into increasingly dense clumps, setting up the scaffolding on which the first stars would eventually form. Gas clouds were slowly contracting, heating up as they collapsed under their own gravity. It was a time of preparation when the universe was quietly organizing itself for the spectacular light show that would come with the birth of the first stars. The first stars were nothing like the sun. When the Dark Ages finally ended and the first stars ignited, they were monsters compared to the stars we see today. These primordial giants, called population 3 stars, were hundreds of times more massive than our sun and burned with incredible intensity. They lived fast and died young, shining for only a few million years before exploding as supernovae. These first stars had a crucial job to do. The Big Bang had created only the lightest elements, but life as we know it requires heavier elements like carbon, oxygen, and nitrogen. The massive first stars served as cosmic factories, using nuclear fusion in their cores to create these heavier elements for exploded at the end of their brief the first time. When they lived, they scattered these newly created elements throughout space, enriching the universe with the building blocks needed for planets and life. The death of these first stars marked the end of the universe's chemical innocence. No longer was space filled only with hydrogen and helium. Now it contained the seeds of complexity, the elements that would eventually form rocky planets, organic molecules, and everything we see around us today. In a very real sense, we are made of star stuff, forged in the nuclear furnaces of these ancient giants that lived and died billions of years before our solar system even existed. The Big Bang created a universe that remembers its past. One of the most remarkable features of the memory of its own cosmos is that it carries within itself history. The cosmic microwave background is like a fossil of the early universe, preserving the conditions that existed when the cosmos was only 380,000 years old. But this isn't the only way the universe remembers its origins. The abundance of light elements like hydrogen and helium serves as another fossil record, telling us about the nuclear processes that occurred in the first few minutes after the Big Bang. The large-scale structure of the universe, the way galaxies are arranged in vast filaments and sheets separated by enormous voids, reflects the tiny quantum fluctuations that existed in the first fraction of a second after creation. Even the expansion of space itself carries information about the Big Bang. By measuring how fast distant galaxies are moving away from us, astronomers can work backward to determine when the expansion began and what conditions were like in the early universe. Every photon of ancient light, every atom forged in those first moments, every large-scale structure serves as a messenger from the past, telling us the story of how our universe came to be. The Big Bang set static. It's a dynamic, a cosmic recycling program. The universe created by the Big Bang are born from clouds and transformed. Stars, evolving system where matter and energy are constantly being recycled of gas and dust, live out their lives fusing lighter elements into heavier ones, and then increasing the complexity return their enriched been going on for over 13 billion years, gradually material to space when they die. This cosmic recycling has and richness of the universe. Our of this recycling program own solar system is a product. The sun is what astronomers call a third-generation star, made from material that has been processed through at least 2 previous generations of stars. The heavy elements in the rocky planets, including Earth, were created in the cores of massive stars and scattered through space by supernova explosions. The calcium in your teeth, the iron in your blood, the gold in your jewelry, all of these elements were forged in stellar furnaces and recycled through the cosmos before eventually finding their way into our planet. This recycling continues today. When our sun eventually dies in about 5 billion years, it will return much of its material to interstellar space, where it may eventually become part of new stars and planets. The Big Bang created not just the initial conditions for the universe, but established the ongoing processes that continue to shape and enrich the cosmos. Billions view as limited. The big of years later, space itself may be infinite, but our Bang created what observable universe has a boundary, which light has had time to reach. We call the observable universe, the region of space from us since the beginning of time. This couldn't travel freely, and light a time when the universe was up, not because space ends there, but because we back to are looking. But beyond this cosmic horizon, space by the Big Bang might be infinite and may continue indefinitely. The universe create extent, containing an infinite number of galaxies, stars, and planets. If this is true, then somewhere out there, far beyond what we can ever see, there might be regions of space where the laws of physics play out in exactly the same ways, creating structures and our place in the cosmos. This possibility raises profound questions about the nature of existence planets remarkably similar to our exact copies of our solar system. Our planet exists somewhere, including possible arrangement of matter might an infinite universe created by the Big Bang, and even ourselves. But these cosmic twins would be so far to remain forever beyond our observe their existence. They would with them or even confirm a way that we could never communicate of the same Big Bang that created our own correlational horizon, products of reality. The Big Bang created a universe where emptiness isn't truly empty. When think of empty a space, we imagine perfect void where nothing exists. But the absolutely Big Bang established a reality far stranger than our intuition suggests. Even in the deepest vacuum of space, far from any stars or galaxies, the fabric of space-time itself is alive with activity. Quantum fluctuations constantly create pairs of particles and antiparticles that flash into existence for the briefest moments before annihilating each other and disappearing back into the void. These quantum fluctuations aren't just theoretical curiosities, they have real, measurable effects on the universe around. The Casimir effect demonstrates that empty space contains energy by showing how two metal plates placed very close together in a vacuum will be pushed toward the quantum each other by activity in the space around them. This vacuum energy may even be connected to dark energy, the mysterious force causing the universe's expansion to accelerate. The Big Bang didn't create emptiness, it created a dynamic, fluctuating quantum foam where the very concepts of something and nothing become blurred at the smallest scales. In this quantum realm, particles borrow energy from the vacuum, exist for impossibly brief moments, and then pay back their energy debt by vanishing. It's as if the universe maintains a cosmic accounting system where even nothingness has substance and structure. Time moves differently in different places throughout the universe. The Big Bang didn't create a universe where time flows uniformly everywhere. Instead, it established a cosmos where time itself can stretch and compress, depending on gravity and motion. Near massive objects like black holes, time moves more slowly relative to regions with weaker gravitational fields. An astronaut falling toward a black hole would experience time normally from their perspective, but to outside observers, they'd appear to slow down and eventually freeze at the event horizon. This time dilation affects the universe. GPS, everything in satellites orbiting Earth experience time slightly faster than we do on the surface because they're in a weaker gravitational field. The difference is tiny, but without accounting for this relativistic effect, GPS systems would accumulate errors of several miles per day. The Big Bang created a universe where time is not a constant backdrop, but a flexible, that responds dimension to the presence of matter and energy. More, even remarkably, the expansion of space itself affects the flow of time. In the early universe, when everything was much closer together and denser, time moved differently than it does today, rate evolution. The cosmic at which changes the pace occurred was dramatically different in those first moments after the Big Bang. Time itself has evolved along with the universe it measures. The Big Bang may have created multiple universes beyond our own. While we can observe only our own cosmic domain, many physicists believe the Big Bang may have been just one of many such events, a vast, creating multiverse of parallel realities. During the period of cosmic inflation, different regions of space might have undergone their own separate Big Bangs, each creating distinct universes with potentially different laws of physics. Indifferent. Of these parallel universes, the fundamental some constants of nature might be slightly the strength of gravity, the mass of electrons, the speed of light itself might vary from one cosmic to another. Some domain universes might be filled with matter we can't imagine, while others might be completely empty, have or collapsed back. This multi suggests that our verse concept after forming on themselves moments. Big Not Bang was a unique event, but part of a process, new. Universes might of cosmic creation eternal constantly be forming, but foam lighting off from the quantum bubbles in an infinite cosmic sea. Each would begin its expansion and evolution, developing own journey of its own galaxies, stars, and perhaps even its own forms of life, all stemming from the same fundamental that created our own cosmos processes. The cosmic web that reveals scatter of the universe. The Big Bang didn't hidden architecture randomly through space. Instead, it established a subtle pattern of density variations that would eventually grow into the largest structures we can observe. Over billions of years, gravity has organized matter into an intricate cosmic web, with galaxies strung along vast filaments of dark matter like pearls on invisible threads. These filaments stretch across hundreds of millions of light years, connecting galaxy clusters and creating a foam-like structure throughout the universe. Between these filaments lie enormous voids, regions so empty they contain almost no galaxies at all. If you could shrink the entire observable universe down to the size of Earth, the cosmic web would look like a three-dimensional spider matter web with concentrated along the strands and vast spaces in empty between. This cosmic architecture tells us about conditions in the very early universe. The patterns we see today, the descendants of tiny quantum fluctuations that existed when the universe was smaller than an atom. Those microscopic ripples in the fabric time have of space grown over cosmic time into the grandest structures in existence, revealing how the Big Bang planted the seeds for everything we see around us. The universe been through has multiple phase transitions. As water can exist as ice, liquid just, or steam depending on temperature, the universe itself has undergone several dramatic phase transitions since the Big Bang. Each transition fundamentally changed the nature of reality, altering how particles behaved and how forces operated. The first, in moments after the Big Bang, all the fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified into a single superforce. As the universe cooled and expanded, this unified force underwent a series of symmetry-breaking events, splitting into the separate forces we observe today. Each breaking was like a cosmic phase transition, fundamentally changing phase transitions may matter, and energy interacted. These have created cosmic defects, strange objects like cosmic strings or magnetic monopoles that could still exist somewhere in the universe today. They might also have generated the matter-antimatter asymmetry that allowed matter to survive ordinary instead of being completely annihilated. Each transition left its mark on the cosmos, creating the complex physics we observe today, the elegant simplicity that existed in the beginning. The Big Bang created a universe that eventually its own history will. While the universe currently preserves evidence of its origins, the cosmic microwave background, and in the abundance of light elements, this won't last forever. The accelerating expansion driven by dark energy means that distant galaxies are moving away from us at ever-increasing speeds. Eventually, they will recede so far that their light can no longer reach us. In the far future, beings living in our galaxy will see only the Milky Way and its immediate neighbors in the night sky. The cosmic microwave background will have cooled and redshifted beyond detection. The evidence that other galaxies ever existed will have vanished beyond the cosmic horizon. Future astronomers will have no way to discover that the Big Bang ever occurred or that the universe contains billions of other galaxies. This cosmic amnesia represents one of the most profound changes the universe will undergo. The very expansion that the Big Bang set in motion will eventually of that race the evidence beginning. Our current era may be unique in cosmic history, a brief window when intelligent beings can look space and peace out into together the story of creation itself. The first moments after the Big Bang may have determined everything that followed. During the period of cosmic inflation, when the universe expanded faster than light, tiny quantum fluctuations were stretched to macroscopic sizes. These fluctuations, which began as random quantum noise smaller than atoms, became the seeds for all the structure we see today. Every galaxy, every star, every planet can trace its origins back to these primordial ripples in space-time. The precise nature of these quantum fluctuations may have been completely random, determined by the fundamental uncertainty principle that governs quantum mechanics. If this is true, then the entire large-scale structure of the universe, the arrangement of galaxies and voids that stretches across billions of light-years, arose from pure chance events that occurred in the first fraction of a second after creation. This means that the universe could have turned out completely different if those initial quantum fluctuations had played out differently. The pattern of matter and energy that led to the formation of our solar system and ultimately to life on Earth may have been determined by random quantum events that occurred when the universe was younger than a trillionth of a second old. In this view, our entire cosmic history was written in those first moments by the quantum dice of creation. The Big Bang created a universe where information cannot be destroyed. One of the most fundamental principles that emerged from the Big. This principle, once created, must be preserved forever. Bang is that information creates profound puzzles about the nature of reality, particularly when it comes to black holes. When matter contains falls into a black hole, what happens to the information Hawking initially proposed that this about its quantum state? Stephen information might be destroyed when black holes evaporate through Hawking radiation, but this would violate the fundamental conservation of information. The resolution to this paradox remains one of the deepest mysteries in physics, potentially requiring new understanding of how space-time and quantum mechanics work together. This information conservation principle suggests that every particle interaction, every quantum measurement, every moment of cosmic history leaves an indelible mark on the universe. Nothing is ever truly lost. The information that describes your thoughts right now, the quantum states of every atom in your body, the precise arrangement of matter and energy around you, all of this becomes part of the permanent record of the universe, preserved in ways we don't yet fully understand. The cosmic horizon problem reveals the universe's mysterious unity. When we look at the cosmic microwave background, we see that it has almost exactly the same temperature in all directions, varying by less than 1 part in 100,000. This presents a puzzle called the horizon problem. Regions of the early universe that were separated by vast distances so far apart that light couldn't have traveled between them somehow ended up at nearly identical temperatures. How could regions that had never been in contact with each other reach such precise thermal equilibrium? The answer may lie in cosmic inflation, the period of faster-than-light expansion that occurred in the first fraction of a second after the Big Bang. Before inflation, all these regions were close enough together to reach the same temperature. Then inflation suddenly stretched space, separating them by vast distances while preserving their thermal equilibrium. This solution to the horizon problem reveals something remarkable about our universe. The fact that we see the same temperature everywhere in the cosmic microwave background tells us that our observable universe, vast as it is, may have originated from a region smaller than a single atom. Everything we can see, from the most distant quasars to the nearest planets, was once compressed into a space so small that quantum effects dominated its behavior. The Big Bang established the fundamental speed at which the universe processes reality itself. Beyond the famous speed of light limit, there exists something even more profound about how quickly the universe can compute its own existence. Every interaction between particles, every quantum measurement, every gravitational wave that ripples through space-time happens at rates determined by the fundamental constants established in those first moments after creation. Think of the universe as a vast processing power of this, the speed of light and boundaries on how quickly cosmic computation. The information processing system, where every particle interaction universal computer is limited by represents a calculation. Every quantum state change a bit of creating natural other fundamental constants. Reality can unfold. A single cubic meter of space can only perform a finite number of operations per second, no matter how much energy you pour into it. This computational limit means that the universe has 13.8 billion years slowly spent the last, calculating its own evolution, working through every possible interaction at the maximum rate allowed by physics. The complexity we see around us, from the intricate structure of galaxies to the delicate chemistry of life, represents the accumulated output of this cosmic computation, processing reality, one quantum interaction at a time since the moment the universal computer first switched on. The Big Bang created a universe where geometry itself tells a story. The shape of space isn't flat like a tabletop, as ours suggest. Everyday experience might instead, the geometry of the universe curves and bends in ways that carry information about it showed us that matter, origins, and ultimate fate. Einstein and energy warp the fabric of space-time, creating the curved geometry we experience as gravity. On the largest scales, the overall geometry of the universe reflects the total amount of matter and energy it curves back on itself, like too much matter space contains. If the surface of a sphere into a would eventually collapse back, creating a closed universe, that big crunch. If there's too little matter, space curves outward like a saddle, creating an open universe that expands forever. The precise balance we observe suggests our universe is geometrically flat, poised but another extremes. This geometric flatness isn't a coincidence consequence of cosmicized perfectly between these two inflation. During that brief period of exponential expansion, any initial curvature in space was stretched so dramatically that it became essentially flat, like how the surface of a balloon appears flat to an ant, even though the balloon itself is curved. The Big Bang didn't just create space, it created space with exactly the right geometry to allow the complex structures we see today to form and evolve. Dark energy may be the universe's way of remembering empty space. The mysterious force driving the accelerating expansion of the universe might be connected to the fundamental properties of empty space itself. Even in regions completely devoid of matter, space appears to contain intrinsic energy density and interward, causing out that push time expansion to accelerate over vacuum. This quantum energy might be related to the fluctuations that constantly virtual create and destroy particles throughout empty space. If this is true, then dark energy represents of its quantum the universe's memory origins, a permanent reminder of the probabilistic foam from which all matter and energy emerged. Every cent cubic's a tiny emitter of empty space contribute amount of dark energy. And as the universe expands and creates more space, the total amount of dark energy increases. The implications are staggering. Dark energy suggests othingness itself, that N but actively particip, not passive, has substance. That empty space is aids in cosmic evolution. The vacuum that emerged from the Big Bang isn't truly empty, but filled with invisible energy that may ultimately determine the fate of everything. As space expands and dark energy grows stronger, it may eventually overcome all apart galaxies' other forces, tyrannies, stars, and even atoms in a scenario relative to black cosmologists called the Big Rip. Regions where the universe contains time generally flows forward throughout moves backward holes. While the cosmos, the extreme gravitational fields around black holes, create regions where the normal flow of causality becomes scrambled. Near the event horizon of a rotating black hole, space-time itself gets dragged along with the rotation, creating areas where the future light cone tilts so dramatically that it overlaps with the past. These regions, called end-erg, between forward this zone world and backward in time, becomes blurred. Aeospheres, the distinction particle entering, might find its through space-time lod line opening back toward path it traces that its own past allow. While this doesn't for the paradox of time travel stories is, it reveals how the Big Bang created a universe where time itself can become twisted and distorted by the presence of massive objects. These temporal distant just theoretical curiosities. They affect Orson's array of matter and energy around the behaviored black holes, influence inward and how energy ensing how material spire holes rotation. The big from the black is extracted the relationship bang establish a fundamental black holes, this between matter energy, space, and time, but in relationship can produce like those effects extreme around that challenge environments, our intuitive understanding of causality itself. Cosmic inflation may have created pockets with universe-brief different physical laws. During the period of exponential expansion that followed the Big Bang, different regions of space might transitions that have undergone phase slightly different times, creating domains with fundamentally different properties. In some of these pocket universes, the constants of nature might be dramatically our own. Different from imagine is millions, where gravity regions of time stronger, crushing matter into exotic states we can barely conceive of. Or domains where electromagnetism operates differently, creating chemistry based on entirely out-of-pocket universes might have more familiar principles. Some than 3 spatial dimensions, while others might have time flows in multiple that direction simultaneously. Domains, these alternate would bed from separate our own by boundaries where the laws of physics themselves change, making travel between communication or direct pocket universe would evolve them impossible. Each of according to its own physical principles and phenomena, potentially developing structures that would be utterly alien to our experience. The Big Bang might have been not just the creation of but the birth of a universe, collection infinite of parallel realities, each playing out the consequences different fundamental of slightly rules. The first stars the create universe's first heavy metal pollution. When the primordial giants that ended the ages expel cosmic darko dead as supernovae, they didn't just create heavy, they scatter elements and them throughout space in the universe yon scent of cosmic pollution's first act. These stellar explosions, shock waves racing through the pristine hydrogen and helium gas that filled early space, mixing the newly forged elements into the cosmic environment. This heavy element pollution was crucial for the formation of the second generation of stars. The trace amounts of carbon, oxygen-heavy elements act and othered as cosmic coolants, allowing clouds to collapse more gas easily under their own gravity. Without this pollution, stars to form as might have continue massive short-lived giants. the heavy elements enabled the formation of smaller, longer-lived stars like our Sun, which could for billions of years. Thed Bernstia also made planets' pollution possible. Rocky worlds like Earth simply cannot form from pure hydrogen and helium. They require silicon for their crusts, iron of other heavy for their cores, and dozens elements for their complex geology. The death of the first stars was therefore essential for the eventual emergence of terrestrial planets and the chemistry of life. In a very real sense, we exist because the early universe learned to pull through itself with that ashes of dead stars. The cosmic web reveals the universe has a direction preferred. While space uniform on appears the largest scales, careful analysis of the cosmic microwave background and distribution of galaxies suggests that the universe the have might a slight preferred orientation, a cosmic axis around which large-scale structures seem to align. This potential asymmetry challenges our assumption that the universe has special no directions built into its fundamental structure. If confirmed, this cosmic axis would represent a kind of universal grain, like the grain a piece of wood, in that influences how matter and energy flow through space. The origin of such an asymmetry might trace back to the very first moments after the Big Bang, when quantum fluctuations in spacetime co-direct have created subtle lional preferences that were then amplified by cosmic inflation. This preferred direction doesn't mean that space is fundamentally different directions, allied different in, but rather that the initial conditions established, settled by the Big Bang, contain to influence the large asymmetries that continue scale structure of the universe today. Like a fingerprint left by moment the of creation, this cosmic grain preserves information about the quantum state. It was smaller of the universe when than an atom. The vacuum of space might be unstable and decayed co-space throughout. Not the universe might fields at quantum any moment. That permeate empty be in their lowest possible energy state. Instead, they could exist in what physicists call a false vacuum, a temporary equilibrium that appears stable but could suddenly transition to a lower energy state. If this happened, it would fundamentally alter the laws of physics throughout the affected region. A false vacuum decay would begin at a single point and expand outward at the speed of light, creating a bubble of completely space with different physical properties. Inside this bubble, atoms might be not able to form, or they might form in entirely. The chemistry, different configurations of life as we know it would become impossible, replaced by physics we can barely imagine. The terrifying aspect of false vacuum decay is that it would be completely undetectable until moment it arrived. The boundary of the expanding bubble would travel at light speed, giving no advance warning of its approach. However, the fact that the universe has existed for nearly 14 billion years without such an event suggests that our vacuum state might be genuinely stable, or at least metastable enough to last for cosmological timescales. Quantum entanglement connects particles across the entire observable universe. The Big Bang created not just space and time, but also established quantum correlations that continue particles separate to linked by billions of light years. When particles interact and separate, they then can remain entangled, meaning that measuring one instantly affects the quantum state of the other, regardless of the distance between them. This cosmic entanglement network means that the universe is not a collection of separate, independent objects, but rather a single, interconnected quantum system where every particle is potentially correlated with every other particle. the apparent separateness we observe is in some sense an illusion created by our astroscopic perspective. At the quantum level, the universe remains unified in ways that Einstein found so troubling he called them spooky action at a distance. The implications extend beyond individual particles to the structure of space-emmer of spacetime itself. Some suggest that the geometry theories G's from patterns of quantum entanglement, meaning that the fabric of reality is woven from invisible correlations between quantum degrees of freedom. In this view, the Big Bang didn't just create particles and fields, but established the entanglement that gives element relationships rise to space and time as emergent phenomena. The universe's expansion creates new space from nothingness. As the universe expands, it doesn't stretch, pulling existing space like on a rubber sheet. Instead, it actually creates new space between existing points, drawing volume, adding to the universe without from any external reservoir. This creation of space from nothing represents of cosmic one of the most profound mysteries. The energy expansion required to create this new space appears to come from the vacuum itself, from even the quantum fluctuations that fill empty regions. As space expands, the vacuum energy density remains constant, meaning that more total energy is created as more space comes into existence. This process has been going on since the Big Bang, steadily increasing the total energy content of the universe. This creation of space and energy from nothingness doesn't violate conservation laws because ational field associate of the gravit with the expansion. The positive energy of newly created space is exactly balanced by the negative gravitational potential energy of the expanding universe, maintaining a perfect cosmic balance sheet universe where something truly bang established A. The big can come from nothing as long as the cosmic accounting remains in perfect balance. The anthropic principle suggests we live in a universe fine-tuned for observers. The precise values of the fundamental constants established by the Big Bang seem remarkably well suited for and life. If the emergence of complexity gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the nuclear forces were different by even small amounts, atoms couldn't form or would be unstable. This apparent fine-tuning raises profound questions about the nature of our universe. Are we incredibly lucky to exist in a cosmos with just the right properties for life? Or are there countless other universes with different parameters and we naturally find ourselves in one where observers can exist? Ick principle suggests that the anthrop universe appears designed for life not because it actually was designed, but because we can only observe universes compatible with our existence. This reasoning leads to the concept of observer selection effects, where the very act of observation biases the properties we measure. Just as life on Earth is perfectly adapted to terrestrial conditions not by design but by evolution, we might exist in a universe with life-friendly properties not because it was created for us, but because only such universes can contain beings capable of asking these questions. The Big Bang may have created not just our universe, but established the conditions that make observers like us possible. The universe contains regions where space itself flows like a river. In the vast emptiness between galaxies, space isn't static, but moves in currents and streams that carry matter along predetermined paths. These cosmic rivers of space-time flow toward massive structures like galaxy clusters, creating highways that guide the movement of gas, dust, and even entire galaxies across billions of years. The flow is so subtle that individual objects within it experience no sensation of movement timescales. These Kerr yet over-cosmicants shape the architecture of the universe. Near black holes, this flow becomes a raging torrent, dragging space-time itself around the rotating mass in a phenomenon called frame dragging. Matter attempting to orbit a black hole finds itself swept along by these space-time currents, unable to remain stationary relative to distant stars. The Big Bang established the dynamic nature of space itself, creating a universe where the stage on which events unfold is itself an active participant in cosmic evolution. These flows of space reveal that emptiness has structure and motion. Like invisible rivers carving canyons through the cosmic landscape, the movement of space-time guides the formation of the largest structures in the universe, creating a hidden choreography that has been unfolding since the first moments after creation. The Big Bang created time zones throughout the universe. Just as Earth has different time zones due to its rotation, the universe contains regions where time flows at different rates relative to each other. Near massive objects, time moves more slowly, while in the vast voids between galaxy clusters, time flows more quickly. This means that a clock placed in the center of our galaxy would tick slightly slower than an identical clock floating in intergalactic space. These cosmic time zones create a complex temporal landscape where simultaneity becomes relative. Events that appear to happen at the same time when viewed from Earth might occur at different moments when observed from other locations in the universe. The expansion of space itself adds another layer to this temporal complexity, as the stretching of space-time affects how time flows in different regions. This temporal diversity means that the universe doesn't age uniformly everywhere. Some regions have experienced more time since the Big Bang than others, creating pockets where cosmic evolution has progressed at different rates. The 13.8 billion year age we assign to the universe is really just the age measured from our particular cosmic time zone, our local reference frame in the vast temporal landscape established. Gravity waves carried by creation itself, messages from the moment of creation. The Big Bang created ripples in space-time that have been traveling through the universe for nearly 14 billion years, carrying information about the earliest waves, far moments of cosmic history. These gravitational, too faint to detect directly, preserve the universe was younger, the memory of events that occurred when, than a second old. They represent the oldest possible signals in the cosmos, predating even the cosmic microwave background by hundreds of thousands of years. Unlike light, which can be absorbed or scattered by matter, gravitational waves pass through everything unchanged, maintaining their original form as they cross billions of light years of space. This makes them perfect messengers from the primordial universe, carrying pristine information about conditions that existed before atoms could form, before the cosmic fog cleared, before any other form of radiation could travel freely through space. The detection of these primordial gravitational waves would open a new window into the first moments after creation, potentially revealing details about cosmic inflation, the nature of space-time at quantum scales, and the processes that establish the fundamental structure of reality. They represent echo of creation itself, the faint whisper of the Big Bang still reverberating through the fabric of the universe. The cosmic microwave background contains hidden patterns that tell stories of the ancient universe. Within the seemingly uniform glow of this primordial light, subtle variations encode information about the quantum fluctuations that existed when the cosmos was smaller than an atom. These tiny temperature differences, measured to incredible precision by sensitive instruments, reveal the seeds that would eventually grow into the galaxies and galaxy clusters we see today. The patterns form a kind of cosmic code with specific angular scales corresponding to different physical processes in the early universe. The largest patterns tell us about the geometry of space itself, while smaller features reveal details about the density of matter and energy during the first few 100,000 years after creation. Scientists can read these patterns like a book, decoding the story of how simple initial conditions evolved into the complex structures we observe. Hidden within these patterns are the signatures of exotic physics that operated in the first moments after the Big Bang. The polarization of the ancient light carries information about gravitational waves from the inflationary epoch, while subtle spectral distortions might reveal energy injection from decaying particles or other high-energy processes. Each measurement adds another page to our understanding of how the universe transitioned from quantum simplicity to classical complexity. The universe's first atoms formed in a cosmic recombination event that changed everything. When electrons finally combined with atomic nuclei to form neutral atoms, it wasn't a gradual process, but a relatively sudden transition through the entire that swept cosmos. This moment caliombination marked the end of the cosmic dark ages and the beginning of a transparent universe where light could travel freely for the first time. The timing of this event was X to the conditions established exquisitely sensitive by the Big Bang. If the universe had contained slightly more rec matter, ombination would have occurred earlier. Had been less, if there matter, it would have happened perhaps later, or not at all. The precise moment when Fermi atoms determined the properties of the cosmic microwave background and set the stage for everything rec that followed. During ombination, the universe transformed from an opaque plasma to a transparent gas in just a few thousand years, a brief moment in. This transition cosmic time released a flood of photons that had been trapped in the primordial plasma since earlier times. These ancient photons, now cooled and redshifted by billions of years of cosmic expansion, form observed today, the cosmic microwave background we carrying with them, the memory of the universe's first great transformation. The Big Bang established the fundamental limits of how fast information can propagate through reality. Beyond the speed of light, there's a deeper limit on how quickly cause and effect can spread through the universe. This ultimate speed limit determines not fast particles, just how can move, but how rapidly quantum can change, how quickly states gravitational influences, how fast can propagate, and even the universe itself can process interactions constituent between its parts. This information speed limit creates boundaries around every point in space, defining regions of causality that expand outwards at the speed of light. Events your light cone cannot influence you, creating a fundamental isolation that preserves the logical structure of cause and effect. The Big Bang didn't just establish these limits, but made them integral to the functioning of physical law itself. The implications extend beyond simple communication delays to the very nature of reality. The finite speed of information processing means that the universe must compute its own evolution in working real time through each quantum interaction at the maximum rate allowed constrained by physics. This computational shapes everything from the stability of atoms to the formation of galaxies, making the speed of light not just a velocity clock speed of the universal computer, Quantum tunneling allows particles to cross barriers that should be impossible to penetrate. The Big Bang established quantum mechanics as a fundamental feature of reality, including the bizarre phenomenon where particles can pass through energy barriers even when they don't have enough energy to go over. They tunnel through the barriers, appearing them. Instead, on the other side, as if that exist. This quantum tunneling plays crucial roles throughout the universe, from enabling nuclear fusion in stellar cores to allowing radioatomic active decay in nuclei. Without tunneling, stars couldn't shine, protons wouldn't be able to overcome their electrical repulsion to fuse together. The sun itself exists because quantum mechanics allows particles to take shortcuts through the energy landscapes that would otherwise keep them apart. The tunneling phenomenon reveals the probabilistic nature of reality established by the Big Bang. Particles don't follow definite paths but exist as clouds of probability that can leak through barriers and appear in classically forbidden regions. This quantum leakage is happening constantly throughout the universe, allowing processes that would be purely impossible in classical reality and enabling the complex chemistry that makes stars, planets, and life possible. The expansion of space creates new vacuum energy throughout the universe. As the cosmos grows larger, the quantum vacuum that fills empty space doesn't get diluted but maintains a constant energy density. This means that expansion literally creates new energy from nothing, adding to the total energy content of the universe without drawing any external source. The energy appears to come from the quantum fluctuations that permeate all of space. This vacuum energy creation doesn't violate conservation laws because it's balanced by the negative gravitational potential energy of the expanding space-time. As more space comes into existence, it creates both positive vacuum energy and negative gravitational energy in exactly equal amounts, maintaining a perfect cosmic balance sheet. The universe can create something from nothing as long as the total remains zero are. The implications staggering for our understanding of cosmic acceleration evolution. Theating expansion driven by dark energy might be powered by this continuous creation of vacuum energy, turning the universe into a perpetual motion machine that feeds on its own growth. As space expands, more vacuum energy comes into existence, which further drives cycle that may expansion, creating a self-reinforcing continue indefinitely. The cosmic web patterns reveals memory, the quantum from era, the vast network of the span-sactic filaments that observable as information universe, preserve about quantum fluctuations that existed when the cosmos was smaller than a subatomic particle. These ancient quantum memories have been stretched and amplified by billions of years of cosmic expansion, transformopic, uncertaining microsecties into the largest structures we can observe. Each filament in the cosmic web traces back to a specific quantum fluctuation in the primordial universe. The thickness, length, and connectivity encode of these structures information about the quantum state of spacetime during the inflationary epoch. By mapping the detail, cosmic web inners can essentially read the quantum memory of the universe, decoding information about physical processes that operated at energy scales far beyond anything in laboratories. This we can reproduce. Cosmic archaeology allows quantum us to study mechanics on scales that dwarf galaxies, the entire using observable universe as an experimental apparatus. The patterns we observe in the distribution of galaxies today are fossils of quantum events that occurred in the first fraction of a second after creation. preserved and magnified by the expansion of space itself. Black holes may be cosmic recycling centers that prevent information loss. When matter falls into a black hole, the information describing its quantum state doesn't simply disappear, but may encode the black hole's surface in a form that preserves every detail. This holographic encoding means that three-dimensional information gets stored on a two-dimensional surface, like a cosmic hard drive that maintains perfect records of everything that enters. As black holes slowly evaporate through Hawking radiation, this stored information may be gradually released back into the universe in highly scrambled form. The process resembles a cosmic shredder and recycling system, where information is broken down into its most basic components and then redistributed throughout space-time. Nothing is truly lost, but everything is transformed beyond recognition. This information recycling may be fundamental to how the universe maintains its quantum mechanical consistency. The Big Bang established conservation laws that require information to be preserved, and black holes appear to be the cosmic mechanism that ensures this preservation even under most extreme conditions. They serve as temporary storage and processing centers in the universe's ongoing effort to maintain its logical consistency. The universe contains natural time, the form of close machines in time-like curves. In extremely regions of war around space-time, particularly rotating black holes and other exotic objects' geometry, the can becomes so twist back that time itself loops on itself. These closed time-like curves create a path through space-time where a traveler could intuitively journey their own past, arriving at an earlier time than when they departed. While such time machines seem to violate causality, they emerge naturally of general relativity that from the equations describe how matter and energy warp space-time. The Big Bang created a universe where time is not a fixed backdrop, but a flexible dimension that can be stretched, compressed, and even fall on itself under extreme conditions. These temporal loops represent the exotic most possibilities in the structure of space-time. The existence of closed time-like curves raises profound questions about the nature of free will and determinism. If the future can influence the past through these temporal loops, then causality becomes a complex web where effects can precede their causes. The universe established by the Big Bang appears to allow for such temporal paradoxes, though provide natural quantum mechanics may prevent them from creating mechanisms that logical contradictions. Cosmic inflation may have created regions where physics operates backwards. During the exponential expansion phase immediately after the Big Bang, different phase transitions at regions of space underwent slightly different times, creating domains, where the arrow potentially of time points in the opposite direction from our own. In these reversed regions, entropy would decrease rather than increase, effects would precede causes, and evolution would run backwards. These time-reversed domains would be completely cut off from our own region of space-time, separated by boundaries where the fundamental direction of temporal flow changes. Communication across such impossible because signals boundaries would need to travel backwards in time relative to one reference frame or the other. Each domain would evolve according to its own temporal direction, creating parallel timelines that diverge from the moment of cosmic inflation. The existence of such regions would mean that the Big Bang created not just multiple universes with different physical constants, but multiple timelines with different temporal orientations. Some universes might be running backwards relative to our own, with stars collapsing into gas clouds, life evolving from complexity to simplicity, and the future flowing toward the past in a cosmic movie played in reverse. The quantum vacuum actively participates in all physical processes throughout the universe. Empty space isn't passive, but constantly interacts with matter and energy through virtual particle fluctuations that borrow energy from the vacuum, exist briefly, and then return their borrowed energy by annihilating. These virtual particles affect the behavior of real particles, shifting energy levels, modifying forces, and influencing the outcome of every quantum interaction. The vacuum's participation in physics means that empty space has measurable properties and can be polarized, excited, and even torn apart under extreme conditions. Near black holes, the vacuum can be ripped into particle pairs, with one member falling into the black hole while the other escapes as Hawking radiation. This process gradually drains energy from the vacuum around the black hole, causing the hole to evaporate over cosmic timescales. The active we call empty space is nature of the quantum vacuum suggests that what really a seething ocean of virtual activity that underlies all of reality. The Big Bang didn't create emptiness but established a dynamic, fluctuating medium that participates in every physical process. In this view, matter and energy are just persistent patterns in the quantum foam, waves on an ocean of virtual possibility that extends throughout the cosmos. The universe's expansion may eventually reverse in a cosmic phase transition we cannot yet predict. While current observations show that dark energy is accelerating the expansion of space, this acceleration might not be permanent. The vacuum energy that drives expansion could undergo a sudden phase transition, similar to how water can suddenly freeze when conditions change. If this happened, the properties of empty space would shift dramatically, potentially causing expansion to slow, stop, or even reverse into contraction. Such a cosmic phase transition would propagate outward from its point of origin at the speed of light, fundamentally altering the physics of space as it spreads. Regions that have undergone the transition would operate under completely different rules, with altered constants of nature and modified interactions between matter and energy. Instead, and new physics would advance boundary between the OL like an invisible wave, transforming reality as it passes. This possibility suggests that our current cosmic era might be temporary, a brief period of stability in universe capable of dramatic transformations. The Big Bang established not just the initial conditions for expansion, but also set up the possibility for future phase transitions that could reshape the fundamental nature of existence itself. The first black holes formed when the universe was still young and dense. These primordial black holes didn't form from collapsing stars, but directly from regions where matter was compressed beyond the critical density needed to create an event horizon. In the chaotic environment of the early universe, random fluctuations in density could create in black holes ranging size from microscopic to millions of times the mass of our sun. These black holes would have had profound effects on cosmic evolution. The smaller heavy ones might apparated completely through Hawking radiation, releasing their energy back into the primordial plasma. The larger ones could have served as seeds around which the first galaxies formed, providing gravitational anchors that helped organize matter into the structures we observe today. Some primordial black holes might still exist, scattered throughout space as invisible remnants of the universe's youth. They would be completely dark, detectable only through their gravitational effects on nearby matter. Finding these cosmic fossils would provide direct evidence of conditions in the earliest moments after creation, offering a window into physics at energy scales we cannot recreate in laboratories. Mechanics. Quantum ensures that identical particles throughout truly the universe are indistinguishable. The Big Bang create where all the cosmos electrons are absolutely identical to each other, all protons share the same properties, and all photons are fundamentally indistinguishable. This isn't just a practical similarity, but a deep quantum mechanical principle that forbids any differences between particles of the same type. This indistinguishability has profound consequences for how matter behaves throughout the universe. When identical particles interact, quantum mechanics requires that we cannot keep track of which particle is which, leading to interference effects and correlations that have no classical analog. The statistics that particles behave govern how identical, whether matter can form stable structures or collapses into exotic quantum states. The perfect in that the big distinguishability of particles suggests Bang-created matter from a uniform source completely, perhaps the quantum vacuum itself. Every electron in your body is identical to every electron galaxy in distantes, not because they were manufactured to the same specifications, but because they are expressions of the same underlying quantum field that pervades all of space and time. The cosmic neutrino background carries information from when the universe was only 1 old. Just second as the cosmic microwave background preserves the after-when glow from atoms first formed, there exists an evanelic radiation more ancient R composed of neutrinos that decoupled from matter when the universe was barely a second old. These ghostly particles have been streaming through space ever since, carrying pristine information about the earliest moments of cosmic history. Unlike photons, neutrinos interact so weakly with matter that they pass planets through entire without being absorbed. This means the cosmic neutrino background has traveled to us virtually unchanged since the first second after creation. Detecting these relic nuational access trinos would provide direct observe to physical processes that occurred when the universe was still dominated rather by radiation than matter. The neutrino background also contains information about the fundamental properties of these elusive particles, including their masses and the number nu of different trinotypes that exist. As these neutrinos continue ancient to cool and redshift with the expansion of space, they represent a fossil record of particle physics from an era when temperatures and energies were far beyond anything we can achieve artificially. Space may have itself fundamental units, making the universe pixelated at the smallest scales. Just images are composed of individual as digital pixels. Space-time might be built from discrete units smaller than anything we can currently observe. At the Planck scale, about 20 orders of magnitude smaller than a proton, the smooth fabric of space-time might give way to a grainy, quantized structure where space and time come in indivisible chunks. This pixelation of reality would mean that there is a smallest possible length and a shortest possible duration, setting fundamental limits on how finely the universe can be divided. Below these scales, the very concepts of distance and time might lose their meaning, replaced by something more fundamental that gives rise to space-time as an emergent property. If is truly space-pixelated, it would resolve many paradoxes in physics by naturally providing cutoffs for calculations that otherwise give infinite results. The Big Bang might have not established just the large-scale structure of the universe, but also its finest scale architecture, operating a cosmic system that runs on discrete units of space and time. The matter-antimatter asymmetry that allows our existence remains one of physics' greatest puzzles. In the first after the Big Bang, equal amounts of matter and antimatter should have been created, and they should have completely annihilated each other, leaving behind energy. Yet only pure somehow, a tiny of matter survive excess, about 1 part in a billion, and this slight imbalance became the foundation for everything we see today. The process that created this asymmetry must have violated certain symmetries that we thought were fundamental to physics. For every billion antimatter particles that were destroyed along one with matter particles survived to become of the cosmic inventory part. Without this seemingly insignificant surplus, there would be no atoms, no stars, no planets, and no life. Understanding how this matter-antimatter asymmetry arose could reveal new physics beyond our current theory's Big Bang create. The conditions for this cosmic lottery, where a random fluctuation or symmetry-breaking event determined that universe would be made of matter rather than antimatter. In parallel universes created by the same process, antimatter might have won, creating cosmic domains where antimatter galaxies shine with anti-light under anti-stars. Dark matter may consist of particles that interact only through gravity and undiscovered forces. While ordinary matter makes up less than 5% of the universe, dark matter comprises about 27%, yet remains completely invisible to all electromagnetic radiation. This mysterious substance appears to interact gravitationally with ordinary matter but passes through it without any other detectable effects. A ghost like that can move mountains. The particles experienced that make up dark matter might forces that ordinary matter cannot feel, creating sector of physics a hidden operating parallel to our own. Dark matter galaxies might exist within and around ordinary galaxies, with their own complex structures and dynamics that we can only detect through their prints. Gravitational finger, these shadow structures be far colloquiate than we more interimagine, with dark matter stars and perhaps dark planets. Even dark life forms existing dimensions of reality we cannot directly. The Big Access Bang created both an ordinary dark matter from the same primordial processes, but somehow kept them largely separate throughout cosmic history. Understanding matter doesn't interact more strongly with ordinary matter could reveal fundamental principles about the structure of reality, and the hidden dimensions exist beyond our that might dimensional experience. Cosmic strings might thread through space like cracks in the fabric of reality itself, the phase. During transitions that occurred as the universe cooled after the Big Bang, defects might have formed in space-time, creating one-dimensional objects of incredible density that stretch across vast distances. These cosmic strings would be thinner than a proton but could extend for millions of light years, carrying the mass of entire galaxies within their impossibly narrow structures. Cosmic strings exist, they would. IFD warp space-time around them in ways distinctive, ensing effects that could creating LD be detected by careful observation of background galaxies. They might also generate the VIB gravitational waves as rate n with each interact other, producing signals that could be detected by sensitive instruments on Earth or in space. The formation of cosmic strings would represent a kind of cosmic welding, where the rapid cooling of the universe froze imperfections into structure of space-time itself. These defects would be permanent scars from the universe's violent youth, preserving information about the energy scales and physical processes that operated in the first moments after creation. The speed of light creates a natural horizon that limits how much of the universe we can ever observe. Beyond a certain distance, galaxies are receding from us faster than light can travel toward us, creating regions of will space that forever remain beyond our observational reach. This cosmic event horizon is from the horizon different around a black hole, but it creates a similar boundary beyond which information cannot flow. As the universe continues to expand and dark energy drives acceleration, this horizon will gradually encompass nearby galaxies, making them disappear from our view. Not light can because they are destroyed, but because their longer reach us across the expanding gulf of space. Future civilizations will inhabit a lonelier cosmos to observe only their local group of galaxies, while the rest of the universe fades into invisible darkness. This observational horizon means that we are living in a special time in cosmic history when the evidence for the Big Bang in existence, the galaxies, is of other still. Visiblers may astronom have future no way to discover that the universe extends beyond their local region, making our current epoch uniquely privileged for understanding the true scoped history and of creation quantum fields that fill all of space, determinate just did and what create matter types of particles can exist. The Big Bang and energy, but established quantum fields that permeate every point in space-time. These fields are like invisible, can be excitions that OCD into, and waves particles are simply localized excitations in fields these underlying. An electron is a rip field, a photon is a wave pulse in the electron field, and every in the electromagnetic type of particle corresponds to its own quantum field. The properties of these, their electric charges, and their other quantum of particles, fields particles, can exist and how they interact with each other. The masses determine what numbers are all determined by the characteristics of their corresponding fields. The Big Bang established and energy are possible. Nude not just the initial conditions for cosmic structure that defines what types of matter evolution, but also the field particles can be created by adding enough energy to excite quantum fields into higher energy states. This is how high energy collisions to create temporary excitations in quantum fields that particle accelerators work using manifest as exotic universe particles. The early, with its extreme temperatures and densities, naturally excited these fields in ways we can only recreate artificially, potentially creating particles that no longer exist in today's cooler cosmos. The anthropic principle suggests that the universe's apparent fine-tuning might result from observer selection effects rather than design. The fundamental constants of nature appear to be precisely calibrated to allow the formation of stars, planets, and life. If gravity slightly stronger were, stars would burn out too quickly for atoms, forces, chemistry complex, nuclear to develop. If the were different, might not be stable enough to form complex molecules. This remarkable fine-tuning could be explained if our universe is just one of countless others in a vast multiverse, each with different values for the fundamental constants. In most of these universes, the constants would not permit the existence of observers, so naturally we find ourselves in one of the rare universes where life is possible. The appearance of design is simply a selection effect, like fish concluding that the universe is perfectly designed for aquatic life. The Big Bang might have created not just our universe, but established the mechanism by which countless universes with different properties could come into existence. In this view, we are not the result of cosmic planning, but cosmic statistics, existing in one of the few realities where existence itself is possible. The cosmic web that connects all galaxies began as quantum foam in the earliest moments after creation. The vast network of filaments that thread through space, connecting galaxy clusters and surrounding its origins to quantum enormous voids, traces fluctuations when the universe was smaller than an atom. These microscopic uncertainties in the quantum vacuum were stretched and amplified by cosmic inflation, eventually becoming the scaffolding on which all large-scale structure would form. Each filament in the cosmic web preserves the memory of a specific quantum fluctuation from the inflationary epoch. The pattern of matter distribution we observe today is essentially a fossil record of the quantum state of space-time, when the universe was incredibly young and dense. By mapping the cosmic web in detail, astronomers can reconstruct the quantum mechanical properties of the primordial universe. Between quantum mechanics, this connection and cosmic architecture reveals the deep unity underlying all scales of existence. The same quantum principles that govern the behavior of individual atoms also determine the arrangement of galaxies across billions of light years. The Big Bang created a universe where the microscopic and macroscopic are intimately connected through the expansion of space itself. Virtual particles in the quantum vacuum might be responsible for the cosmological constant and dark energy. Even empty space is filled with quantum fluctuations that create virtual particle pairs, which briefly borrow energy from the vacuum before annihilating and returning the energy. This process gives empty space a measurable energy density, which, according to general relativity, should contribute to the expansion of the universe. However, calculations of the vacuum energy density give results that are enormously larger than the observed value of dark energy, creating what physicists call the cosmological constant problem. The energy density of empty space should be so large that it would cause the universe to expand at a rate that would prevent any structures from forming. Yet the actual expansion rate is much more gentle. Resolving this discrepancy might require new physics that explains how the quantum vacuum energy is regulated or canceled by unknown mechanisms. The Big Bang might have established not just the initial conditions for cosmic expansion, but also set up the delicate balance between quantum vacuum effects and gravitational forces that allows the universe to expand at exactly the right rate for structure formation and life. And so we drift through these cosmic mysteries, each fact a gentle wave carrying us deeper into the profound story of our existence. From the first moment when time began to tick to the quantum foam that underlies all reality, we have traced the threads that connect us to the very fabric of creation. The Big Bang was not just an event that happened long ago, but the ongoing foundation of everything we experience, every breath we take, every thought that passes through our minds. As these cosmic truths wash over you, let them carry you toward rest, knowing that you are part of a story so vast and beautiful that it spans from the smallest quantum fluctuations to the largest structures in space. In the gentle rhythm of your breathing, you echo the expansion and contraction that 14 billion years has shaped the universe for nearly in the quiet beating of your heart. You participate in the same fundamental processes that power stars and galaxies across the cosmos. The atoms that form your body carry within violence and stellar them the memory of cosmic death. Every carbon nucleus in your DNA was forged in the heart of a dying star, compressed and heated to temperatures that dwarf the center of our sun. When those ancient giants exhausted their fuel and collapsed in spectacular supernova, they scattered these precious heavy elements across space in expanding shells of glowing gas. For millions of years, these stellar ashes drifted through the cosmic void, slowly cooling and mixing with clouds of primordial hydrogen. Eventually, gravity gathered this enriched material into new stellar nurseries, where second and third generation stars could form with the chemical complexity needed to create rocky planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all bear the signatures of nuclear furnaces that burned billions of years ago. You are quite literally made of stardust, carrying within your very atoms the legacy of cosmic cycles that have been repeating since the first massive stars ignited in the early universe. This stellar recycling program continues today throughout the cosmos. Giant molecular clouds collapse to form new stars, which live out their lives fusing lighter elements into heavier ones, then return their enriched material to space when they die. Each generation of stars builds upon the chemical heritage of those that came before, slowly increasing the universe's inventory of complex elements. The Big Bang created a cosmos capable of learning and growing, accumulating chemical wisdom through billions of years of stellar evolution. The expansion of space creates a kind of cosmic loneliness that grows stronger with time. As dark energy drives the acceleration of cosmic expansion, galaxies that are currently visible to us will eventually recede beyond our observational horizon. Their light will become so redshifted that it fades into the infrared and then into radio waves too faint to detect. Future astronomers living billions of years from now will inhabit a much emptier seeming universe, able to observe only their local group of gravitationally bound galaxies. This cosmic isolation has profound implications for the future of scientific discovery. The evidence that convinced us of the Big Bang's reality, the cosmic microwave background radiation, and the abundance of light elements will eventually become undetectable as the universe expands and cools. The grand narrative of cosmic evolution that we can piece together today may become impossible to reconstruct for civilizations that arise in the far future. In this sense, we are living during a golden age of cosmology when the universe still preserves clear evidence of its violent birth and tumultuous youth. The night sky we see today, filled with distant galaxies and ancient light, represents a temporary window into cosmic history that will gradually close as space continues to expand. We are perhaps the last generation that will ever be able to observe the full scope of creation spread out before us in the darkness between stars. The quantum uncertainty that governs the smallest scales of reality played a crucial role in seeding the largest structures in the universe. During cosmic inflation, quantum fluctuations in the vacuum were stretched to macroscopic sizes, creating tiny variations in density that would eventually grow into galaxies and galaxy clusters. These fluctuations were genuinely random, governed by the fundamental uncertainty principle that makes it impossible to predict the exact outcome of quantum measurements. This means that the detailed arrangement of matter in our universe, the specific pattern of galaxies and voids that we observe, arose from quantum coin flips that occurred when the cosmos was younger than a trillionth of a second. If we could somehow rerun the Big Bang, the same physical laws would operate, but the random quantum fluctuations would play out differently, creating a universe with a completely different large-scale structure. Tonight we've journeyed through the most profound story ever told, the tale of how everything came to be from a single moment smaller than an atom. From cosmic inflation to quantum foam, from the first atoms to the vast web of galaxies, each discovery has carried us deeper into the mystery of our existence. As you drift toward sleep, remember that you are not separate from this cosmic story, but an integral part of it, made of ancient starlight and quantum dreams, forever connected to the magnificent universe that gave you life.